What's coming off around here?
Ain't you guys playing railroad anymore today? There's a landslide, a new cut.
Hi, and welcome to Fun with HO Scale Stuff. This is episode 12 and part 2 of DCC Under the Hood. And I mentioned at the conclusion of the previous episode 11 that I would present some kind of circuit that would explain how the signal used on DCC is created. And recall from that episode that I had explained it was that the DCC signal is an AC square wave signal. So how do you create that from DC? So you had a simple explanation that the circuit would start out with, well, a DC source, of course. So you'd have some kind of DC supply, and that outputs some kind of a voltage, V plus, and some kind of reference we call ground. And that's a DC signal. It's not an AC signal. So how does that get converted? Well, first let me show you that you could take, say, a switch and put this VC, the DC voltage here, and then put some kind of load on that, and then tie that back to the ground. As long as the switch is open, there's no current flowing. So if we're looking for current, it's just non-existent. But the minute you close that switch, then the voltage is applied to this load, and there's a current in that direction back through the ground. But if you look at this little simple diagram and you say, well, let's add to the DC 2 switches, and we'll do it like this. We'll put one here, and we'll put one here. And we'll say, here's our load, a potential current. We have a V plus coming here, and a ground reference here. And now we've got a configuration where, in order to have current flow through the load, here you have a load. Sorry if that's hard to read, I'm sloppy. Then the only way to get the current to flow through the load is if you close both switches. So let's suppose we close both switches here, and now we've got current. If we open either one of them, no current. Next thing you want to see to try to explain how this little circuit here could be used to create an AC is we'll take a DC, and we're going to call, our V out and our ground reference and D, that's V plus. And now we're going to take 2 of these switches and we're going to move them around. I'm going to put one here, and that'll be the V, and I'm going to put one here. Let me put it over here. And that'll be, like that. Switch like that. And that's going to be our ground. And then we're going to take this over here and call that a load. And then move that back over here. And so now it's just reconfigured a little bit, but the reason why I started with this is because we're going to add 2 more just like this. And we're going to put one here, and we're going to put one here. And instead of ground on this one, let's go down here. So this was V plus. We're going to make this one ground. So we've got ground here and V plus here. So we wouldn't want to close both those switches at the same time or we'd have a dead short. We're going to do the same thing with the V plus. We're going to route that over here, like this, and like this. So again, you wouldn't want to close both these switches because we've got V plus here, we've got V plus here, we've got ground here, we've got ground here. So what's happening is that if I actually look at this switch here would reverse where the V plus would be applied. So in this case, you might have your V plus here, and then of course this switch would be closed here. So these two switches kind of work together. So if I close this, then I'd have ground up here, and notice that that's reversed of what we had here, where we had V plus here and ground here. So if I close, on the other hand, these two switches, I have V plus here, and I'd have ground here. So by adding these simple switches and closing them in the right sequence, I can create an alternating application of either voltage or ground on the load. And by doing that in a sequential fashion, what happens is that the current that we were creating is both directions now. It's alternating. It depends on the switch setting. So if V plus here, then the current is going down through the load. If the V plus is here, the current is going up through the load. So ultimately what happens then is that despite where the source, the creator of this AC signal exists, in this case it would exist in our throttle. And then the throttle would have the DC source in it, and it would be generating this AC signal out here. And depending on how it does it, how long the switches are closed, for instance, you can have long and short signals being generated with bidirectional currents. So that if this was some ground reference created by doing the switching we just discussed, this ground reference is not that ground reference. It's just an average of the highs and lows by alternating the current on the load. So in effect, there's some average center, and in this case, the current, while you're above this reference, the current is going that way, and when you come below that reference, the current's going the opposite direction, which is the case with AC. And that's a square wave. So the signal is then an AC square wave. Now, the next thing I want to do is show you how something called a decoder would take this kind of a signal and make it into something it can use. This is a schematic of the Arduino motor shield. The motor shield is the device that's most commonly used to create DCC signals by applications like DCC++ or DCC-EX. The reason why is this chip right at the center. The chip is called an L298, and the L298 device is a dual half-bridge device driver. It's got two what's called H bridges or full bridges that create the ability to do the switching of two outputs, and the switching in this case is done exactly the same way as I have indicated, showing the simple switches in my previous discussion. The only difference is it's using transistors, not physical switches, and the transistors are controlled by these logic elements that show our AND gates. And so an input signal on these inputs
or for that matter, these inputs, control how the outputs are going to be polarized. So by switching the inputs, the polarity of the outputs is going to change. Now, this device was typically used for motor controls because the motor will go forward or reverse depending on which way the current is being applied. So switching the current in that case controls the direction of rotation of the motor. But in this case, as I've shown in my previous discussion, it's used to actually create an AC square wave as a signal for the DCC.
So now we've introduced the concept of a DCC signal on the tracks that's comprised of an AC square wave. Given that, the question then is, now that this signal is applied, it doesn't come with a ground reference, it's just floating. So it floats in respect to the throttle. And the throttle had its own ground from its own power supply. So that was not an issue. But with the decoder, it becomes sort of an issue, and it has to figure out how to extract this coded durations that indicate the zeros and ones, but it also has to be able to convert this signal into a DC source that can power up the decoder to begin with. So just to present to you very crude approximation that is in a circuit that would at least explain the basic function of the decoder. I wouldn't want to get into the details of how to actually design a decoder, but what I would like to do is just present an overarching explanation that you can comprehend the basics of what that decoder has to do in order to be able to deal with this AC square wave. Let's start with the how does it extract the actual signal itself, the pulses, the durations. So the first thing I want to introduce is a circuit component called a diode. The diode has a circuit diagram like that. And a diode, if you're not familiar with it, is a device that allows current to pass only in one direction. It's a traffic cop. So let's say that the diode has the capability then of taking an AC signal and chopping it. How would it do that? Well, let's go back to the AC signal that we were discussing earlier. And let's say that we want to know what that duration is so we can extract the code of either a 0 or a 1. And so as the signal is passed through the diode, let's say that there's some reference voltage that's neither high nor low. It's sort of in the middle. And I think it's as long as there is active signals on the track, there will be a reference voltage. It's just the central voltage between the highs and lows. And so it's the crossover point, if you will, of the two currents. And also for definition, let me just say that for the high portion of the signal, I'm going to say the current goes in that direction. And for the low portion of the signal, I'm going to say that the current goes in the opposite direction, which is the essence of AC. It's alternating current. So we have this kind of situation here, and the diode can actually allow only currents that are in the high portion to pass through. So if we did a circuit somewhat like this with say a resistor, or what we just call the load, where the signal is being applied across from the track, from the rails, across this diode, then the signal that's coming out of this, the signal actually being detected by the decoder here as a voltage, we'll just call it V naught, across the resistor is looking like the top half of this signal. So it's going to be that sort of thing, so that it can then take these durations and measure them using whatever method. There's various ways to do that, but you'll see one when I discuss in a bit how my monitor, my DCC monitor works. I'll get into more detail about how I chose to determine what those pulse widths are, but I don't know that that's how a decoder does it. Just there's many ways it could possibly do that. But at any rate, now it has some signal with respect to its reference voltage that is actually toggling up and down and has durations. So it can then extract zeros and ones and reassemble whatever the packet information was that was placed onto the track. Now I said, again, the decoder has a second issue, is that it needs to power up. So it needs some kind of a DC voltage. So this signal that we have with the AC square wave has to be rectified in order to do that. So what we do is we take the signal that we have toggling up and down through some neutral point. And when I say rectified, I mean we're going to take and flip everything that's below reference. We're going to flip it up so that the signal then becomes a signal that looks like this. In other words, this portion of the signal in this area, with respect to the reference voltage, has been flipped up because of the rectification. So what does it is it's a bridge rectifier or something equivalent to the bridge rectifier. So this becomes then a DC signal, and this signal can be applied to the decoder as V plus, and then this reference voltage becomes its V minus. So the decoder now has a DC signal. So I want to show you the how that works. So we have a signal coming in, we have the track, and we take, here's our A, and then we take from here, we call it B, and we're going to move these signals around a little bit to make us some room, so that this signal initially, let's say that initially the track has this kind of polarity in this region, the upper region. And it's seeing the positive part, and we're going to step through this. So we're going to say that this is going to be tied to a diode, and that being a positive is going to allow the current to pass through the diode. So the diode, which would only permit current in one direction, is going to allow that to go to the decoder. So let's say we now have a voltage going to the decoder, and then we're going to we'll have to have a current going back that goes to return. But we want to pass that. We're going to pass that through a diode just for grins. So this return is our reference voltage, and for the moment. And so we're going to do something a little shady. We're going to put another diode on here, and we're going to call that is our return. And you'll see why I did that in a moment. But at any rate, you could see that if the current is flowing this way, that when the current returns, it's got to go back through here and go back to B, from A to B. So that's how that would work if we were only going to be using a signal like this to power the decoder. But we don't want to do that. It's not a very it's not a very healthy thing to be hitting a decoder with a chopped square wave. So we want to refine this a little bit. So what the next step is to add another diode here and another diode here. Okay, they're a little sloppy. I apologize for that, but you get the idea that we're channeling the currents. So in this case, let's talk about again, when the positive was here, it couldn't come through this diode because it only allows current to go that way. So it had to go this way. And again, it couldn't go back through that diode because, same reason, it goes up to here. And as it comes back, it could potentially go through that diode, except that there's a positive voltage here. So there's no encouragement, if you will, for the currents to go back that way. So what they do is they go through this nice path here from what they are essentially a higher voltage to back to the neutral of the track. So we have, again, that same path working, even though I added two diodes. But now what happens when I put the negative here and I put the positive here? So now there's a positive down here, and current wants to flow this way. So the current wants to flow this way in that case. So now we're talking about this portion of the signal. And in this portion of the signal, with the currents reversing on that AC, we got a push coming this way. Well, it can't go through that diode, so it's got to go through this diode, and up it goes to the plus. And it wants to come back. It's going to return this way. And now we've got a plus here. So it's not going to be enticed to go that way. So what's going to go through this diode, and it won't go through that again because there's a plus up here. So it's going to go back to the track here. So as long as this sine wave keeps switching, this is called a bridge rectifier, and that rectifies the signal, as I had indicated here, to become a DC signal. Now there's more to it. I'm saying this explanation is very crude. It's an approximation. I mean, there's so much other circuit involvement in creating a very nice DC signal that the decoder can use. But at any rate, this crude circuit is demonstrating that there's a DC voltage applied to the decoder, and that DC has a reference voltage. And that reference voltage is the same reference voltage that we were saying is applied and used by the decoder to be able to see these step waves and extract those durations. So that's pretty much, in a nutshell, an approximation, again, of the circuitry that is used on behalf of the decoder. And just one more little statement while we're looking at a decoder here. Obviously, one of the functions of the decoder is to run the motors. And so we have some motor out here. And so as long as the decoder is able to understand the packets are going to tell this decoder direction and speed. And so the motor is actually being applied a voltage that's being generated by the decoder, and the decoder is generating it from the DC that it extracted from the signal itself. So it's kind of, you see this is very much tied together in terms of the principles of how a decoder works. So that's it. The next thing I'd like to do is explain how I take an AC square wave and use it to monitor the packets that are on the tracks, so that we can actually see that happening. I'll demonstrate how it works. So what you see here is an Arduino Uno that I'm using as a controller for what I call my DCC monitor application. The controller itself talks to the PC through the USB port, and is powered here, gets a voltage supply from its power supply. This little chip here is the 328P microcontroller from Atmel. It's a fairly functional little device, and so far I've been able to accomplish quite a lot with respect to the real-time data processing that I had to do in order to convert the AC square wave coming from a track generated by the throttle, and be able to convert those to packets to be able to transmit them back up to the PC via the USB communications. In order to debug code, basically, that's why I added 2 LEDs to this Arduino, because at points it's you don't have an in-circuit emulation capability with these Arduinos, at least not to my knowledge. And so some really crude troubleshooting techniques are inserting breakpoints, which are actually stop loops that turn on a particular sequence of the LEDs and blink them in a certain fashion so I can understand what the actual code is doing. But that aside, this circuit over here that you see is the conditioning circuit that takes the AC square wave DCC signal and converts it to DC pulses. Now, I'll show you the DC pulses and the signal on the scope so you can see the two of the signals, and I'll show you the application as well. But the current state of the application is that, it was mostly just created by me for the sake of just a hobby. It's just one of those additional parts of fun with HO scale stuff. And so, electronics has always been an interest for me, and being able to actually see these DCC packets was just kind of a fun little thing to do. So anyway, moving along, I just briefly talk about this circuit over here, the conditioning circuit, because I want to show you how it parallels the previous discussion we just had about how to convert a DCC signal. This is the circuit diagram for the conditioning components that I have on the board here. The DCC signal coming in, as I stated, it's a AC square wave. So the first thing I need to do is clip that square wave. So I'm only interested in the upper half cycle of every one of the square waves. And so what you see here are these 2 diodes. This diode is the reverse diode, and there's one inside the optocoupler right there. And basically what that does is it makes the AC square wave see this 1K resistor as a simple load, but the diode in the optocoupler is only passing the upper half of the square wave. The signal, once applied to the input of the optocoupler, is going to cause, every time you see a positive half cycle where there's current flowing, is a light generated from that LED within the optocoupler. And then this light-sensitive AND gate, well, actually it's a NAND gate, every time it sees the light pulse, it turns on its output. And by doing that conversion, it's turning it on into, on this side of the optocoupler, 5 volts. So the 5 volts is a good input for the Arduino. And so here's the output that's going to the Arduino, and the Arduino is seeing this on its input, and the input is looking at it as a rising and falling edge, and the rising edge and falling edge are being used to gate a timer on and off, and the timer data is being used to correlate to a duration. And as it was stated earlier, the duration of the pulses is what codes the ones and zeros. So in this case, I don't care about converting this to a DC. What I do care about is converting the AC square wave to a series of pulses that I can convert back into packets of DCC commands, and then transmit those DCC commands back up to the PC application. I'll show you that and I'll show you the signals. What the scope here is showing you is that this is the signal, the DCC signal directly taken from the track. And the scope is showing the square waves. It also shows the ground reference. At the ground reference that you see is basically in the middle of the two signals. Are symmetrical about the ground, positive and negative, and that the total voltage differential peak to peak is 30.4 volts measured by the scope. So basically that means then that the power cab uses about a 15 volt source, DC source, and that 15 volts plus and 15 volts minus is creating a differential voltage of about 30 volts. The signal you see here is the conditioned signal of the AC square wave. This is basically ground referenced to the Arduino, and that the signal being created for the Arduino is about roughly a 5 volt signal.
So what you see here is the Windows application that I created, which is communicating with the Arduino. The Arduino is collecting the real-time data and transmitting it up to the application when it's instructed to. So this application, of course, it's just a tool I'm using to play around with, and it's hardly complete. It's not really very professional, and many other disclaimers for the moment. In fact, it still has, the system itself has certain bugs that under certain conditions, it's impossible for me to collect a signal because of some sort of ground issue, but I'm still chasing that bug. But at any rate, this functions right now, and the way it begins is to communicate with the Arduino. I select the COM port that has the USB connection on it. Connected shows that the connection for some reason didn't make it that time. Let's do it again. COM3. Okay, now it's connected. That's a bit finicky too, so it's got to be ironed out. But anyway, I can start the collection using 400, and it has done the collection. And what you see, it just counts the collected packet, and then whether the packet was valid or not. In this case, it was valid. And you can see the packet address. What's happening is that the NCE power cab is addressing a particular location on the track. All the packets are addressable to a particular decoder. In this case, 3 is the address. That's the default, which the NCE power cab is trying to speak to. It's not in service mode, so service mode is false. And the command itself is shown here in hexadecimal. If you're not familiar with hexadecimal, I apologize for that lack of clarity, but just for the sake of this presentation, this is some numeric representation of the binary packet. That would be the ones and zeros that were extracted using the conditioning circuit, processed by the Arduino real-time processing, and sent up to this application on the PC.
So that concludes the discussions on DCC circuitry that I offered as a kind of crude explanation of how these DCC signals are created. The initial part of the discussion was a lead up to explain that the DCC electrical signal is actually an AC square wave that is created by the throttle side, and that on the decoder side, I showed a number of circuitry approximations that show how the signal is extracted and how the decoder is powered up. Then I mentioned at the conclusion of that discussion about the ones and zeros that constitute the packet. So part 3 of DCC Under the Hood is in an upcoming episode. We'll discuss just what that packet information is and I'll step back in that episode and again show you the packet that was extracted by my DCC monitor, hexadecimal data, and I'll show you what that actually meant so you can get a clear idea of how those bits and the ones and zeros are being utilized by the decoder. So if any of this has been interesting at all, and you haven't skipped the entire presentation, please leave a like, and if you haven't already, please subscribe. I do appreciate any comments anyone can leave. If you have questions, I love to answer your questions. So don't hesitate. Go ahead and leave me a comment with any questions or tell me what I could have done better. I appreciate those kinds of comments as well. So thank you for watching. And once again, if you don't mind, please like and subscribe. Thank you.